At the largest visible scale, the speed of light sets the boundary of everything that can be observed. Light moves through empty space at about 300,000 kilometers per second. This speed is immense by ordinary standards, yet the universe is so large that even light requires vast stretches of time to cross it. Every distant object therefore appears through old light. A nearby star is seen as it was years ago. A remote galaxy is seen as it was millions or billions of years ago. The farther the source lies, the earlier the visible image belongs in cosmic history. The observable universe is the region from which light or other signals have had enough time to reach an observer since the early universe became transparent. It is not necessarily the whole universe. The full extent may be much larger, and it may even be infinite. Observations define only the part connected to the present by travelling information. Beyond that boundary, light has not yet arrived, so no telescope can receive it. This limit does not arise from weak instruments. It follows from the finite age of the universe and the finite speed at which information moves. The universe is about 13.8 billion years old. A simple first impression suggests that the most distant visible matter should lie about 13.8 billion light-years away. The actual present distance is greater because the large-scale geometry of space changes while the light is traveling. Matter, whose ancient light reaches Earth today, can now be roughly 46 billion light-years away in every direction. This gives the observable region a present diameter of about 92 billion light-years. These distances describe where the matter is now within the standard cosmological model, not the path length measured by a single fixed ruler through unchanging space. The visible boundary is often called the particle horizon. A horizon in cosmology is not a physical wall, it is a limit created by the history of light travel. Matter beyond the particle horizon may exist under the same broad laws of nature, but its signals have not had time to arrive. The horizon depends on the observer's location and time. Every observer carries a surrounding observable region defined by the signals that can reach that place. On very large scales, no central viewing point is required. Each location has its own horizon. The oldest light that can be observed directly does not come from the first instant of the universe. In the earliest period, matter is hot, dense, and filled with free electrons. Photons scatter repeatedly and cannot travel freely across great distances. After about 380,000 years, the universe cools enough for electrons and atomic nuclei to form neutral atoms. Light then moves much more freely. The remaining radiation from that transition is observed as the cosmic microwave background. It arrives from every direction and forms a nearly uniform glow with small variations in temperature. The cosmic microwave background marks a surface of last scattering rather than a solid shell. Each detected photon travels from a region where it last interacts strongly with matter before beginning its long journey. Different directions point to different regions of that ancient surface. Telescopes measure slight temperature differences that reflect early variations in density. These patterns provide evidence about the young universe and about the later formation of galaxies and larger structures. The radiation has traveled for most of cosmic history, carrying information that remains limited by the speed of light. Some information reaches even farther back through indirect evidence. The abundance of light elements, the distribution of galaxies, and the statistical pattern of the cosmic microwave background preserve traces of conditions earlier than the release of freely traveling light. These records do not allow ordinary images of the first moments. They allow physical models to be tested against measurable consequences. The distinction remains important. Light speed limits direct observation, while preserved effects allow cautious reconstruction of earlier conditions. Astronomical observation is therefore also observation through time. A map of the distant universe is not a picture of all regions at one shared moment. Nearby structures appear relatively recent, while remote structures appear increasingly young. Deep surveys reveal galaxies during earlier stages of development because their light begins its journey long ago. The sky combines many ages into one field of view. The speed of light creates this layered record without changing the local physical laws along the way. The finite travel time of light also limits causal influence. A cause can affect a distant region only after a signal crosses the space between them. Regions separated so widely that no signal has passed between them remain outside one another's causal contact during that interval. This principle supports the idea of a light cone, a geometric description of events that can influence a location or be influenced by it. Events inside the past light cone can send signals that arrive now. Events outside it cannot yet contribute information to the present observation. This causal structure prevents information from appearing everywhere at once. Even the brightest event remains unknown beyond the region reached by its radiation. Distance alone does not erase the event, but distance combined with limited travel time, delays every possible record of it. No known object with mass travels through empty space at the speed of light. Matter can approach that speed, but increasing energy is required as it moves faster. Light in a vacuum follows the limiting speed built into space-time. This same limit applies to every form of information and to gravitational disturbances. Observations of distant cosmic events agree closely with this shared causal speed. At the cosmic horizon, the truth about light speed becomes quiet and precise. The observable universe is not defined only by what exists, but by what has had time to become known through arriving signals. Every point of light carries a record shaped by distance and duration. The outer boundary remains a boundary of access rather than a final edge of reality. Within it, the visible cosmos forms an immense archive, and the speed of light determines how that archive opens across time. Across the largest scales, the universe does not remain fixed while light travels through it. Space expands, carrying widely separated galaxies farther apart, even as each beam of light continues to move locally at the same constant speed. This distinction is central to modern cosmology. The light does not slow because the distance grows, and it does not need to exceed its usual speed to cross an expanding region. Instead, the geometry through which it moves changes during the journey. Cosmic expansion is described by the growth of distance between locations that are not held together by strong local forces. Galaxies inside the same gravitationally bound group do not simply swell with the universe. Stars do not drift away from their planets because of cosmic expansion, and atoms do not expand with space. Gravity, electromagnetism, and the other binding forces dominate at these smaller scales. Expansion becomes important across immense distances, where matter is distributed in large structures separated by broad regions of space. A useful description treats the universe as having a changing scale. The scale factor is a quantity that expresses how average cosmic distances grow with time. When the scale factor increases, two galaxies that remain at rest relative to the general cosmic flow become farther apart. This does not require either galaxy to move through its local surroundings in the ordinary sense. Their separation increases because the large-scale geometry between them changes. Light still passes every nearby observer at about 300,000 kilometers per second in a vacuum. This local measurement remains the same whether the observer lies in a galaxy between galaxies or near the edge of the observable region. General relativity allows the total distance between faraway regions to increase in a way that does not behave like ordinary motion through one fixed background. For that reason, extremely distant galaxies can recede from one another at an effective rate greater than the speed of light without violating the local speed limit. No nearby object overtakes a local light beam. The growing separation belongs to the expansion of the large-scale geometry. As light crosses expanding space, its wavelength grows with the scale of the universe. A wavelength is the distance between repeating parts of a wave. When that distance becomes longer, the light shifts towards the red end of the visible spectrum or beyond visible light into infrared and microwave wavelengths. This effect is called cosmological redshift. It differs from an ordinary change caused only by a source moving through nearby space. Motion can also produce redshift, but cosmic redshift records the expansion that occurs while the light is traveling. A galaxy observed at high redshift appears through light that begins its journey when the universe is smaller. During the long passage, the expanding geometry stretches the wave. The energy carried by each detected photon is lower than it is at emission because photon energy is related to frequency, and frequency decreases as wavelength increases. This does not mean that the photon gradually encounters friction. Empty space does not resist it like air resists a moving object. The change follows from the evolving geometry and from the way energy is defined in an expanding universe. The travel time cannot be found by dividing a present distance by the speed of light, as though the distance remains unchanged. The source is closer when the light begins its journey, while the space between source and observer continues to grow. A photon may move toward an observer at every local point and still find the total separation increasing for part of its path. Later changing conditions can allow the distance to decrease until the photon finally arrives. Its local motion remains steady throughout, but the large-scale distance depends on both that motion and cosmic expansion. This behavior creates several kinds of cosmological distance. The distance to a galaxy at the time its light is emitted differs from its distance when the light is received. The present distance to the matter in that galaxy differs again from the distance inferred directly from brightness or apparent size. Cosmologists use carefully defined measures because no single ordinary ruler spans the entire expanding universe. Each distance answers a different observational question, and each is calculated within a model tested against many kinds of evidence. The rate of expansion also changes over cosmic time. In the early universe, matter and radiation strongly influence how rapidly the scale changes. As the universe evolves, the relative importance of its contents changes. Observations indicate that expansion is now accelerating on very large scales. The simplest widely used explanation includes dark energy, a name for the component associated with this acceleration. Its underlying physical nature remains uncertain. Measurements of distant supernovae, the cosmic microwave background, and the distribution of galaxies support the general picture, while continuing studies refine the expansion history. Acceleration affects which signals can ever arrive. Some distant regions emit light that reaches an observer, now yet light emitted by those same regions at a much later cosmic time may never arrive. The expanding separation can grow so persistently that the remaining distance never closes. This produces a cosmic event horizon, a limit related to future communication. It is distinct from the particle horizon, which concerns signals that have had time to arrive since the early universe. Both horizons arise from the interaction between finite signal speed and changing cosmic geometry. The measured speed of light, therefore, remains constant locally, even while cosmic distances behave in unfamiliar ways. Expansion does not push light from behind or drag it forward. It changes the relationship between widely separated places as the beam passes through successive local regions. Every small part of the journey obeys the same local rule, while the total path reflects the history of the universe. At this scale, light becomes both a messenger and a record of expansion. Its arrival time reveals the changing distance it has crossed, and its stretched wavelength preserves part of that history. The redshift of a remote galaxy does not provide a simple speed through static space. It carries information about when the light begins, how the scale of the universe changes, and how the geometry develops before the signal reaches its destination. The constant local speed and the changing cosmic distance remain fully compatible, joined by the structure of spacetime itself. Beyond the crowded regions of galaxy clusters, light travels through immense intergalactic voids. These are broad regions where matter is unusually sparse, though they are not completely empty. A few atoms occupy each cubic meter in many parts of this space, and even that small amount varies from place to place. Thin gas, faint radiation, weak magnetic fields, and scattered particles remain present. The void appears dark because very little matter produces or reflects visible light, yet it still forms part of the physical universe. The large-scale distribution of matter resembles a cosmic web. Galaxies and clusters gather along filaments and sheets while voids open between them. Gravity draws matter toward denser regions over long periods, leaving the spaces between increasingly underdense. These low-density regions can extend for tens or even hundreds of millions of light-years. A photon crossing such a distance spends most of its journey far from stars, planets, and bright clouds. Its path is quiet in appearance, but it is not entirely free from interaction. In a nearly empty void, light moves locally, at the vacuum speed. No material medium fills the space strongly enough to slow the beam in the ordinary sense used for glass or water. The photon still passes through weak gravitational fields and through the changing geometry of the expanding universe, but its local speed remains constant. The great travel time comes from the enormous distance, not from resistance. Even a region that seems almost empty can require millions of years to cross. The gas inside intergalactic space is mostly hydrogen and helium. Much of it is ionized, meaning that electrons are separated from atomic nuclei. The gas is extremely thin, so collisions are rare compared with those in a planetary atmosphere or a laboratory chamber. Some regions are cool by cosmic standards, while others are heated by shocks and by energetic radiation from galaxies. The temperature can be high even when the total heat content is low, because temperature describes the average energy of individual particles rather than the total number of particles present. Light can interact with this gas through absorption and scattering. A photon with a suitable energy may be absorbed by an atom or ion moving an electron to a higher energy state or removing it completely. Other photons may scatter from free electrons. Because the density is so low, most light passes through without any interaction at all. Over enormous distances, however, even rare encounters can leave measurable traces. Astronomers detect these traces as narrow, dark features in the spectra of distant sources. A spectrum separates light according to wavelength. When light from a distant quasar passes through several clouds of intergalactic hydrogen, each cloud removes a small set of wavelengths linked to hydrogen. Cosmic expansion shifts the position of these features according to the distance and age of the cloud. The result is a sequence of absorption lines known as the Lyman alpha forest. It provides a record of diffuse matter distributed between galaxies. The forest reveals that apparently empty space contains structure at many scales. Dust is far less common in voids than inside galaxies, but some grains can escape from galactic environments. These tiny solid particles may absorb shorter wavelengths and re-radiate energy at longer wavelengths. They can also scatter light away from its original direction. The effect is usually weak in the emptiest regions, yet careful measurements must consider it. A small amount of dust spread across a vast distance can alter the apparent brightness and color of a remote object. Intergalactic magnetic fields are also weak, and their origin remains uncertain. Observations place limits on their strength and suggest that some magnetism exists even far from galaxies. Light itself carries no electric charge, so a steady magnetic field does not bend its path directly in the way it bends the motion of charged particles. The field can still influence the plasma through which light travels, and under certain conditions this can alter polarization. Polarization describes the orientation of the light's electric field. Measurements of polarization help researchers study both the radiation and the thin matter along its path. High-energy photons face additional interactions. Gamma rays from distant galaxies can collide with low-energy photons that fill intergalactic space. If the combined energy is sufficient, the interaction can produce an electron and its antimatter counterpart, a positron. This process removes the original gamma ray from the beam. The effect depends on the photon energies and on the density of background light. It limits how far some very energetic radiation can travel before being absorbed. The background light in intergalactic space comes from several sources. The cosmic microwave background fills the universe with ancient radiation. Starlight emitted across cosmic history and infrared radiation from dust also contribute to a faint extragalactic background. These photons are individually weak, but they are widespread. They form a thin sea through which more energetic light must pass. Most visible light travels through it almost undisturbed, while some gamma rays interact more readily. Gravity also alters the route of light through the void. Although matter is sparse, no region is perfectly uniform. Filaments, galaxy groups, and dark matter concentrations create curved paths through spacetime. A light ray passing near these structures can be deflected. This gravitational lensing may magnify, stretch, or split the image of a distant source. In voids, the lower density can produce a subtle effect in the opposite direction, making some images slightly dimmer or changing their apparent shape by a small amount. The travel time can also shift because the gravitational environment changes along the route. Light passing through a deeper gravitational region and light crossing a more empty region can arrive at slightly different times even when their geometric paths seem similar. These differences are generally small, but precise observations can detect them across cosmological distances. The effect allows the distribution of visible and invisible matter to be studied without direct contact. Through the intergalactic void, light remains remarkably persistent. Most photons continue without collision, carrying information from galaxies far beyond the empty region. A few are absorbed, scattered, delayed, or redirected. Those rare changes become evidence. The darkness between galaxies is therefore not a blank interval. It is a thin and structured environment whose gas radiation fields and gravity leave delicate marks on every sufficiently long journey. Within a galaxy, light no longer crosses a nearly empty expanse. It enters a system shaped by hundreds of billions of stars, clouds of gas, drifting dust, stellar remnants, magnetic fields, and a larger mass that does not emit light directly. These components gather under gravity and form a rotating structure extending for tens of thousands of light years. The environment remains mostly empty, yet it is far denser than an intergalactic void. A spiral galaxy contains a bulge, a flattened disk, and an extended halo. The disk holds many visible stars together with gas and dust arranged along spiral patterns. The bulge contains older stars packed more closely around the center. The halo reaches much farther than the disk and includes scattered stars, globular clusters, hot gas, and dark matter. Light passing through each region meets a different balance of density, radiation, and gravity. The journey through a galactic disk is shaped strongly by dust. Interstellar dust consists of tiny, solid grains made from materials including silicates, carbon-rich compounds, and frozen coatings in colder regions. The grains are much smaller than sand. They absorb and scatter light, especially at shorter wavelengths. Blue light is removed more readily than red light, so a distant star can appear redder than it truly is. This effect is called interstellar reddening. Dust can also hide regions from visible telescopes. Thick lanes cross the bright faces of many spiral galaxies, creating dark bands against the glow of stars. These bands are not empty gaps, they are clouds filled with gas and dust that block the light behind them. Infrared radiation can pass through some of this material more easily, allowing instruments to detect stars and warm dust concealed at visible wavelengths. Gas forms another part of the galactic environment. Most of it is hydrogen with helium and smaller amounts of heavier elements. Some gas is cold and molecular, some is neutral and atomic, and some is ionized by radiation. The ionized gas contains free electrons and nuclei. Each phase interacts with light differently. Cold clouds absorb narrow ranges of wavelength, while hot gas can emit ultraviolet or X-ray radiation. Stars fill the galaxy with a wide spectrum of light. Cool stars radiate strongly at red and infrared wavelengths. Hot stars produce more blue and ultraviolet light. Stellar explosions and compact remnants add bursts of X-rays and gamma rays. The combined radiation field changes from place to place. Near young star clusters, energetic ultraviolet light can ionize surrounding gas. In older regions, the light is softer and more evenly spread. A beam traveling through this mixed environment may pass untouched for long distances, then cross a dense cloud where absorption becomes stronger. The total effect depends on wavelength. Radio waves can travel through many dusty regions that block visible light. Infrared light is less strongly scattered than visible light. Ultraviolet radiation is absorbed readily by gas and dust. X-rays can penetrate some clouds, while the most energetic gamma rays interact through different high-energy processes. Galactic magnetic fields extend across large regions of the disk and halo. These fields are weak compared with magnets used in life, but they influence charged particles over enormous distances. Light carries no electric charge, so the field does not pull it sideways. However, light passing through ionized gas can have its polarization rotated. This process is known as Faraday rotation. The amount of rotation depends on the magnetic field electron density and wavelength. Radio observations use this rotation to map invisible magnetic structure. The fields often follow broad spiral patterns, though they also contain tangled and turbulent regions. Exploding stars, stellar winds, and moving gas stir the plasma and reshape the field. The resulting structure affects cosmic rays, which are high-energy charged particles moving through the galaxy. These particles do not travel in straight lines because magnetic fields bend their paths. Dark matter contributes most of the mass in the galactic halo. It does not absorb, emit, or reflect detectable light in the ordinary way. Its presence is inferred from gravity, especially from the motion of stars and gas. Outer parts of galaxies rotate faster than visible matter alone can explain. A large extended distribution of unseen mass provides the simplest model, consistent with many observations. Although dark matter does not interact with light directly, its gravity affects the geometry through which light travels. A massive galaxy can bend light from a more distant source. The result may be a distorted arc, a magnified image, or several images of the same background object. Within a single galaxy, smaller gravitational deflections also occur, though most are subtle. These effects reveal mass, whether or not that mass shines. The center of a large galaxy often contains a supermassive black hole. Most of the time, the black hole itself remains dark, but nearby gas can become extremely bright as it falls inward and heats. Light passing close to the central region follows curved paths determined by gravity. Farther away, the influence joins the combined gravitational field of stars, gas, and dark matter. Travel time across a galaxy remains long, even at light speed. A beam crossing a disk 100,000 light-years wide requires roughly 100,000 years in a static description. The path may be longer if gravity bends it or if scattering redirects it. Most photons move through vacuum between interactions. Their local speed remains unchanged, while absorption, re-emission, and scattering can delay the arrival of energy. When a photon is absorbed by dust or gas, the original photon ends. The material later releases energy, often at another wavelength and in another direction. The replacement is not the same photon continuing more slowly. This distinction explains why light can appear delayed through a complex medium, even though every freely moving photon travels at the local vacuum speed. Across galactic space, darkness and brightness overlap. Stars provide countless sources dust removes. Selected colors gas writes narrow lines into spectra. Magnetic fields rotate polarization and gravity curves the route. The speed of light remains constant in each local vacuum, but the information carried by light is transformed by the material and structure of the galaxy. By the time a beam leaves the far side, it may preserve not only the nature of its source, but also a layered record of everything it crosses. Inside interstellar clouds, light meets matter thin by earthly standards, but dense enough to reshape every signal that passes through it. These clouds occupy regions between stars and contain gas dust magnetic fields and traces of complex molecules. Some appear diffuse, while others become dark against brighter backgrounds. Their structure changes over time under gravity, radiation, turbulence, and the pressure of nearby stars. Most of the gas is hydrogen. In warmer regions, hydrogen exists mainly as separate atoms. In colder and denser regions, pairs of hydrogen atoms form molecules. Helium is common, while heavier elements appear in much smaller amounts. Carbon, oxygen, nitrogen, silicon, iron, and other elements provide pathways for cooling and chemistry. Dust grains contribute only a small fraction of the total mass, yet strongly influence how light moves through the cloud. A diffuse cloud may contain a few dozen or 100 particles in each cubic centimeter. A dense molecular cloud can contain thousands or millions in the same volume. These densities remain far below that of air near Earth's surface. This matters because a cloud can extend across many light years. A small interaction chance repeated over a long path can produce a strong effect. Visible light entering a cloud is scattered and absorbed by dust. Scattering changes the direction of the light without necessarily removing all of its energy. Shorter blue wavelengths are scattered more efficiently than longer red wavelengths. As a result, stars viewed through dust often appear dimmer and redder. The same process can create a soft blue glow around bright stars when scattered light reaches an observer from the surrounding cloud. Absorption removes photons from the original beam. Dust grains take in the energy and become slightly warmer. They later release this energy as infrared radiation. The original visible photon does not continue at a reduced speed. It ceases to exist in the absorption event, and new photons leave the grain later in different directions and usually at longer wavelengths. This exchange changes the color and timing of the radiation that emerges from the cloud. The total dimming is called extinction. It combines absorption and scattering out of the direct line of sight. Extinction depends on the amount and type of material along the path. Astronomers compare the observed colors of stars with the colors expected from their temperature to estimate how much dust lies between the source and the telescope. These measurements help map clouds that might otherwise remain difficult to see. Gas also leaves narrow marks in a spectrum. Atoms and molecules absorb only photons with particular energies. Each species, therefore, produces a recognizable pattern of lines. Neutral hydrogen, ionized calcium, sodium, carbon monoxide, and many other substances can be identified in this way. The lines reveal chemical composition, temperature, density, and motion within the cloud. When different parts of a cloud move toward or away from the observer, the absorption lines shift slightly in wavelength. These shifts show that interstellar clouds are not still. They contain streams, rotating fragments, expanding shells, and turbulent eddies. Some are compressed by stellar winds or supernova shock waves. Others collapse gradually under gravity. Light records these motions without disturbing the cloud very much. Dense clouds become especially dark at visible wavelengths because dust blocks light from stars behind them. Their interiors can remain cold, often only several degrees above absolute zero. At such temperatures, many atoms and molecules settle onto dust grains as thin, icy coatings. Water, carbon monoxide, carbon dioxide, methane, and other compounds can freeze onto the surfaces. Infrared light reveals absorption features created by these ices. The interiors are shielded from much of the ultraviolet radiation produced by nearby stars. This protection allows fragile molecules to survive longer. Observations detect simple organic molecules and more complex carbon-bearing compounds in many clouds. Their presence does not imply biology. It shows that chemical reactions proceed even in cold, sparse environments when enough time dust surfaces and suitable energy sources are available. Radiation still enters from several directions. Starlight reaches the outer layers. Cosmic rays penetrate more deeply and can ionize atoms and molecules. These high-energy particles help drive chemistry inside regions where ultraviolet light is weak. The ionization also allows gas to remain partly connected to magnetic fields, even when most particles are electrically neutral. Magnetic fields thread through interstellar clouds and influence their shape. Charged particles spiral around field lines and transfer some of their motion to neutral gas through collisions. The field can slow collapse in certain directions or guide material into filaments. Polarized light from background stars helps reveal the field orientation because elongated dust grains tend to align with the magnetic environment. Their absorption and emission become slightly stronger along preferred directions. Light traveling through ionized portions of a cloud may experience dispersion. Different radio frequencies then travel with slightly different effective delays because free electrons respond to the changing electric field of the wave. Lower radio frequencies are delayed more than higher ones. Pulses from distant pulsars show this effect clearly. By comparing arrival times across radio frequencies, astronomers estimate the total number of free electrons along the path. Scattering can also broaden a pulse. Small irregularities in electron density redirect parts of the radio signal along slightly different routes. Some portions travel farther and arrive later than others. A sharp pulse becomes stretched in time. This does not mean that any local photon moves below the vacuum speed while traveling freely. The delay arises from interactions with the plasma and from the increased lengths of scattered paths. A cloud can therefore act as a filter, a screen, and a record. It removes some wavelengths, redirects others, adds infrared emission, rotates polarization, and changes arrival times. The effects depend on density, composition, temperature, ionization, grain size, and magnetic structure. Each alteration contains information about the material between the source and the observer. Within interstellar clouds, the speed of light remains a local constant. Whenever light moves freely between interactions, the measured signal may still arrive later, weaker, redder, or more diffuse. Matter does not simply force the same photon to crawl through the cloud. Instead, countless microscopic events reshape the path and replace absorbed energy with new radiation. The cloud becomes visible through these changes, and light emerges carrying a quiet record of the hidden material it has crossed. Inside, a starlight begins in an environment far denser and hotter than interstellar space. Gravity pulls matter inward while pressure from hot gas and radiation pushes outward. When these influences remain balanced, the star keeps a stable form for long periods. The light that eventually leaves the surface carries energy created deep within this layered structure, but the journey from the center to open space is neither direct nor rapid. In a star like the Sun, the central region is compressed to extreme density and temperature. Hydrogen nuclei move rapidly and collide. Under suitable conditions, some overcome their electrical repulsion and join through nuclear fusion. Fusion combines light nuclei into heavier ones and releases energy because the final particles have slightly less mass than the particles that formed them. The missing mass appears as energy. Much of this energy first emerges in the motion of particles and in very energetic photons. These first photons do not travel straight to the surface. The stellar interior is filled with charged particles, including free electrons and atomic nuclei. Matter exists mainly as plasma, a state in which electrons are no longer bound to individual atoms. A photon moves only a short distance before interacting with an electron or nucleus. It may scatter, be absorbed, or be replaced by new photons. Each interaction changes its direction and often changes its energy. The outward movement, therefore, resembles a random walk. A photon may travel a small distance, scatter backward, move sideways, and then scatter again. The original photon created near the center does not remain intact throughout the entire journey. Its energy passes through countless interactions and is redistributed among many particles and photons. Estimates of the total escape time vary with the model, but energy can require tens of thousands to hundreds of thousands of years to move from the solar core to the surface. This long delay does not mean that light moves slowly between interactions. Whenever a photon travels freely through the local plasma, it moves at the local speed of light. The delay comes from the extremely short paths between interactions and from the repeated changes in direction. A straight route across the Sun would take only a few seconds at light speed. The actual transport of energy lasts far longer because the interior is opaque. The inner region where radiation carries most of the energy is called the radiative zone. Here, photons and particles repeatedly exchange energy. High-energy radiation produced near the core is gradually transformed into lower-energy radiation. The temperature also falls with distance from the center. Energy flows outward because the inner layers are hotter than the outer layers, but the flow remains slow and diffusive. Farther outward in a sun-like star, radiation becomes less efficient at carrying energy. The gas is cooler and more opaque, and large masses of plasma begin to move. This region is called the convective zone. Hotter material rises, releases energy, cools, and sinks again. Convection transports energy through the physical motion of matter rather than through radiation alone. The surface pattern of bright cells and darker borders reflects this restless movement beneath the visible layer. The visible surface is known as the photosphere. It is not a solid boundary. It is a thin region from which photons can finally travel outward without being scattered again inside the star. Below it, matter is too opaque for direct view. Above it, the density falls enough for light to escape into space. The photosphere of the Sun has an average temperature of about 5,800 degrees on the absolute temperature scale. The spectrum leaving the photosphere is close to that of a hot, dense body with a broad distribution of wavelengths. The Sun emits visible light strongly, but it also releases infrared and ultraviolet radiation. Cooler stars emit a larger share of their energy at longer wavelengths, while hotter stars emit more at shorter wavelengths. Color, therefore, provides information about surface temperature, though dust and other effects along the path can alter the observed result. Dark absorption lines cross the smooth stellar spectrum. These lines form when cooler gas above the photosphere removes photons at particular wavelengths. Each chemical element produces a characteristic pattern. By studying these patterns, astronomers determine the composition of stellar atmospheres. The lines also reveal temperature, pressure, rotation, magnetic fields, and motion toward or away from the observer. Above the photosphere lies a thinner layer called the chromosphere. Its density is low, but its temperature begins to rise with height. During a total solar eclipse, the chromosphere can appear as a narrow, reddish rim. Farther outward lies the corona, an extremely thin atmosphere extending millions of kilometers into space. The corona reaches temperatures of more than 1,000,000 degrees, far hotter than the visible surface. The exact processes that produce this heating are studied through observations of magnetic fields, waves, and small releases of energy. Magnetic fields shape much of the activity in the outer stellar atmosphere. They emerge through the surface twist, reconnect, and guide hot plasma into loops. Sunspots appear darker because strong magnetic fields reduce the upward transport of heat in local regions. Flares release energy suddenly and produce radiation across a wide range of wavelengths. These events alter the brightness of the star without changing the basic local speed at which light escapes once it reaches transparent space. Different stars move energy outward in different ways. Massive stars often have convective cores and radiative outer regions, while smaller stars can contain much deeper convection. Very low-mass stars may be convective through nearly their entire interiors. These differences affect how fuel is mixed, how long the star remains stable, and how its surface light changes over time. The light leaving a star is therefore the final stage of a long chain of energy transport. Fusion begins the process in the central regions. Radiation carries energy through repeated interactions. Convection may move it through rising and sinking plasma. The photosphere releases it into open space, while the outer atmosphere adds lines, bursts, and high-energy emission. Once the light escapes, it travels freely, carrying evidence of the temperature composition, motion, and magnetic structure of the star that produced it. Its steady glow therefore reflects an hidden history of pressure collisions, repeated absorption, and gradual outward energy transfer. Within a planetary system, light moves through a region shaped by one central star and by the many bodies held around it through gravity. Planets, moons, rings, asteroids, comets' dust, and thin streams of charged particles occupy paths that appear orderly but remain active. Most of the volume is close to vacuum, yet the system is filled with radiation, magnetic fields, scattered matter, and changing shadows. The central star supplies nearly all visible light in the system. Its radiation spreads outward in every direction, becoming less intense with distance because the same energy is distributed across an ever larger area. A planet close to the star receives far more energy than one farther away. This difference helps shape surface temperatures, atmospheric conditions, and the state of water, ice, or gas on each world. Light crossing the space between the star and a planet usually travels without collision. The travel time depends mainly on distance. Light from the Sun reaches Earth in a little more than 8 minutes. It reaches Jupiter in roughly half an hour to nearly an hour, depending on the changing positions of the planets. It requires several hours to cross the outer reaches of the solar system. Planetary systems are not static arrangements. Each body moves along an orbit while light is traveling. Observations therefore record where a planet was when the light left it, not where it is at the instant the signal arrives. Spacecraft navigation accounts for this delay. Commands sent from Earth require time to reach a distant probe, and returned data require additional time to come back. The exchange can take minutes or hours, preventing immediate control. A planet becomes visible mainly by reflecting starlight, though warm planets also emit infrared radiation. Reflection depends on the surface and atmosphere. Bright clouds can return a large fraction of incoming light, while dark rock ocean or carbon-rich material absorbs more. The fraction reflected is called albedo. A high albedo makes a body appear bright at visible wavelengths, though its apparent brightness also depends on size, distance, and phase. Phase describes how much of the illuminated side is visible from a given location. A planet can appear full half-lit crescent-shaped or nearly dark as its position changes relative to the star and observer. Phase changes do not result from the object producing more or less light. They arise from the changing angle at which reflected starlight reaches the observer. Atmospheres alter reflected and transmitted light. Some wavelengths are scattered, some are absorbed, and some pass through. When a planet crosses in front of its star, a small part of the starlight may filter through the upper atmosphere. Molecules remove narrow bands of wavelength, leaving a spectral pattern. This method allows astronomers to investigate atmospheric composition on planets that cannot be seen as resolved disks. Clouds and hazes can hide deeper layers. Tiny particles scatter light and may flatten or weaken chemical features in a spectrum. A thick haze can make a planet look smooth even when the atmosphere below contains many gases. Observations across visible infrared and ultraviolet wavelengths help separate these effects. The interpretation remains careful because several different atmospheric structures can sometimes produce similar signals. Moons create additional paths for light. They cast shadows across planets and pass into planetary shadows during eclipses. A moon with no thick atmosphere reflects light directly from rock ice or dust. An icy surface can be bright while dark volcanic material absorbs more strongly. Fine dust can scatter light in complicated ways, making the surface appear different at different angles. Rings form broad, thin structures made from countless particles. In the solar system, these particles range from tiny grains to larger blocks of ice and rock. Each piece reflects light separately. The combined brightness depends on the angle of the rings, the size and texture of the particles, and the position of the star. Dense rings can cast shadows on the planet and block light passing through them. Asteroids and comets occupy more varied orbits. Asteroids generally contain rock metal or carbon-rich material. Their irregular shapes produce changing brightness as they rotate. These variations allow rotation periods and approximate shapes to be estimated. Surface minerals also absorb selected wavelengths, so reflected spectra reveal broad clues about composition. Comets change strongly as they approach the star. Heat causes frozen materials to release gas and dust, forming a surrounding coma and one or more tails. Dust reflects sunlight, while gas can glow after absorbing energy from ultraviolet radiation. Charged particles in the solar wind shape an ion tail that points broadly away from the star. The dust tail curves more gently because larger grains retain more of the comet's orbital motion. The solar wind is a stream of charged particles flowing outward from the star. It carries magnetic fields through the planetary system and interacts with atmospheres, moons, comets, and planetary magnetic fields. Light is not pushed aside directly by this wind, but radio signals can be delayed or distorted as they cross changing concentrations of electrons. Measurements of these effects reveal the structure of the plasma. Dust between planets also scatters sunlight. In the solar system, this creates a faint glow called zodiacal light. The dust comes from collisions among asteroids and from material released by comets. Individual grains are sparse, but together they form a broad cloud around the Sun. Their scattered light becomes visible under dark conditions when the geometry is favorable. Gravity bends light slightly as it passes near planets and the central star. The effect is strongest near the most massive body. Radio signals sent past the Sun follow curved paths and experience a small additional travel delay caused by spacetime curvature. Precise measurements of this delay agree with general relativity. Planetary gravity can also produce tiny lensing effects, though these are usually difficult to observe. Within a planetary system, the speed of light remains constant in local vacuum, while distance, motion, reflection, absorption, plasma, and gravity shape what finally arrives. Every visible planet, moon, ring, asteroid, and comet is seen through delayed light. The system appears immediate, yet every image belongs to a slightly earlier state. Light crosses the empty intervals quickly, then gathers information from surfaces, atmospheres, particles, and fields before continuing outward as a record of a changing celestial environment. Near massive objects, light travels through regions where gravity changes the geometry of space-time. General relativity does not treat gravity simply as a force pulling light from a straight path. Mass and energy curve space-time, and light follows the straightest route within that curved geometry. To a distant observer, the route appears bent. The local speed of light in vacuum remains constant, but direction, travel time, and measured frequency can change. A planet produces only slight curvature, while a star creates a stronger one. White dwarfs, neutron stars, and black holes create deeper gravitational regions because large masses occupy small volumes. The closer light passes to such an object, the more strongly its path bends. Light does not need mass for this effect. It carries energy and momentum, and its motion follows the geometry through which it passes. The bending of starlight near the Sun provides an early test of general relativity. During a total solar eclipse, stars close to the hidden solar disk appear slightly displaced from their usual positions. Their light passes through curved space-time near the Sun before reaching Earth. Modern measurements use radio signals, spacecraft tracking, and distant compact sources to test the same effect with greater precision. A larger mass can act as a gravitational lens. When a distant source, a massive foreground object, and an observer lie near the same line. Foreground, gravity redirects light from the background source. The observer may see several images, a bright arc or a nearly complete ring. The pattern depends on the mass distribution and the relative positions of source, lens, and observer. A gravitational lens can magnify a source that would otherwise remain too faint to detect. It can also distort the apparent shape of galaxies. Galaxy clusters produce especially strong lensing because they contain enormous amounts of visible matter and dark matter. By measuring the distortions, astronomers reconstruct the mass distribution. This method reveals matter through gravity even when it emits no detectable light. Smaller objects can create microlensing. The images are too close together to be separated, but the background source temporarily brightens as the lens moves across the line of sight. A star planet or compact remnant can produce such an event. The changing brightness follows a characteristic pattern, allowing dark or distant objects to be detected through gravity. Gravity also changes the time required for light to travel. A signal passing near a massive body arrives slightly later than it would if space-time were flat. This extra interval is called the Shapiro delay. It appears in radar signals sent toward planets when the path passes close to the Sun. The signal still moves locally at light speed, but curved geometry changes the relation between distance and time. Two light rays following different routes around a gravitational lens can arrive at different times. One path may be longer and another may pass through stronger curvature. If the background source changes in brightness, the same change can appear in several lensed images at different times. These delays help measure the lens and provide information about cosmic distances. Light, climbing away from a massive object, loses frequency as measured by an observer farther from the gravitational field. This effect is called gravitational redshift. The wavelength becomes longer and each photon is measured with less energy. Light falling inward is measured at a higher frequency and becomes gravitationally blue-shifted. The change does not arise from friction or a loss of local speed. It reflects the different rates at which clocks run in regions of different gravitational strength. A clock deeper in a gravitational field runs more slowly relative to a clock farther away. This gravitational time dilation affects every physical process, including the rate at which light waves are emitted. Radiation leaving the surface of a white dwarf therefore appears slightly redshifted. Near a neutron star, the effect is much stronger because the mass is compressed into a sphere, only tens of kilometers across. Neutron stars contain matter at extreme density. Their magnetic fields can be exceptionally strong and their surfaces can produce X-rays and gamma rays. Light emitted from the far side may curve around the star enough to reach an observer. More than half of the surface can sometimes be visible at once. The apparent shape and brightness of rotating hot regions depend on space-time curvature and the star's motion. Near a black hole, curvature becomes more severe. The event horizon is the boundary beyond which no future directed light path can escape to distant space. It is not a material surface. Light crossing it locally continues forward normally, but every possible route leads farther inward. A distant observer never receives a signal emitted from inside the horizon. Light emitted just outside the horizon can still escape if it begins along a suitable outward path, but it becomes strongly redshifted. Its arrival is increasingly delayed when described using the time of a distant observer. The source appears to fade as the radiation shifts to longer wavelengths and becomes harder to detect. This does not mean the falling object remains physically frozen at the horizon in its own local experience. Outside a non-rotating black hole lies a region where light can orbit at a particular radius. These circular paths are unstable. A small disturbance sends the light either outward or inward. Strongly bent rays near this region help form the bright ring and dark central shadow seen around supermassive black holes. The dark area is larger than the event horizon because many light paths are captured. A rotating black hole adds further structure. Rotation drags nearby spacetime around with it, an effect called frame dragging. Light moving with the rotation and light moving against it follow different paths. The shadow and nearby plasma depend on the black hole's mass rotation and viewing angle. Observations remain consistent with the broad predictions of general relativity, while measurements continue to test details. Across every gravitational region, light preserves the same local vacuum speed. Gravity changes geometry rather than forcing light to accelerate or decelerate in the ordinary mechanical sense. Bending delay redshift, magnification and capture arise from space-time structure and observer position. Light, therefore, becomes a precise probe of mass-revealing planets, stars, dark matter, neutron stars, and black holes through the paths that gravity permits across the surrounding sky. Within a planetary atmosphere, light enters a layered mixture of gases, particles, clouds, and changing temperature. The atmosphere is much denser than interplanetary space, yet its density falls with height. Near the top, molecules are widely separated and collisions are uncommon. Deeper down, pressure increases, particles meet more often, and the path of light becomes more strongly shaped by the material around it. The first change often comes from refraction. Refraction is the bending of light as it passes through regions where its effective speed differs because of interactions with matter. In an atmosphere, density usually increases downward, so the path curves gradually rather than changing direction at one sharp boundary. A star near the horizon can therefore appear slightly higher than its true geometric position. The same effect allows the Sun to remain visible for a short time after it has passed below the horizon. Refraction does not mean that photons lose their local identity and drift slowly through the air. The electromagnetic field interacts with bound electrons in molecules, and the combined response produces a lower effective propagation speed for the wave. Between interactions, light still moves at the local vacuum speed. The measured delay belongs to the repeated response of matter across the path. Scattering changes the direction of light. In a clear atmosphere, molecules scatter shorter visible wavelengths more strongly than longer wavelengths. Blue light is therefore redirected across the sky more efficiently than red light. The daytime sky appears blue because scattered light arrives from many directions. Near sunrise or sunset, direct sunlight crosses a longer atmospheric path. Much of the blue light is removed from the beam, leaving more orange and red light to continue toward the observer. Larger particles scatter light differently. Water droplets, ice crystals, dust ash, and haze can redirect many visible wavelengths with similar strength. Clouds therefore appear white or grey rather than strongly blue. Their brightness depends on thickness, droplet size, lighting angle, and the amount of light absorbed within them. A thick cloud can reflect much of the incoming sunlight, while allowing only a weaker diffuse glow to pass through. Absorption removes selected wavelengths from a beam. Atmospheric gases have molecular structures that respond to particular energies. Water vapor absorbs strongly in several infrared bands. Carbon dioxide absorbs infrared radiation at other bands. Ozone absorbs much ultraviolet light high in the atmosphere. Oxygen, methane, nitrogen compounds and many other gases also produce distinctive patterns. These absorption features allow atmospheric composition to be studied from a distance. Not every wavelength reaches the surface equally. An atmospheric window is a range of wavelengths that passes through with relatively little absorption. Visible light crosses Earth's atmosphere efficiently, which supports surface illumination and vision. Some radio wavelengths also pass through well. Much ultraviolet radiation is blocked, and large parts of the infrared spectrum are absorbed by water vapor, carbon dioxide, and other gases. The atmosphere also emits radiation. Molecules and particles with thermal energy release infrared light according to their temperature and composition. A planet, therefore, sends energy outward even when its reflected starlight is weak. The emerging spectrum contains both broad thermal emission and narrower features created by atmospheric gases. These features reveal temperature differences between layers as well as chemical composition. Clouds complicate this signal. A high, cold cloud emits less infrared radiation than a warm surface below it. A low, warm cloud emits more. Thick clouds can hide the surface entirely at some wavelengths. Thin clouds may partly transmit light while adding their own scattering and emission. Accurate interpretation requires models that include altitude, particle size, temperature, and coverage. Aerosols are small particles suspended in the air. They may come from dust, sea spray, volcanic eruptions, smoke, chemical reactions, or material arriving from space. Aerosols can brighten a planet by reflecting sunlight or warm it by absorbing radiation. Their effect depends on composition and height. Some remain for days, while others persist for months or years in stable atmospheric layers. Light also changes polarization as it passes through an atmosphere. Scattering can favor certain orientations of the electric field. Reflections from clouds, oceans, ice, and land produce additional polarization patterns. These patterns help distinguish surfaces and atmospheric particles even when direct images lack fine detail. Polarization provides information that brightness alone cannot supply. During an eclipse or transit, starlight can skim through the edge of an atmosphere. The long, slant path increases the amount of gas encountered. Molecules absorb their characteristic wavelengths, while clouds and haze reduce the overall signal. The resulting transmission spectrum contains a filtered record of the atmosphere. Similar methods are used to study planets orbiting other stars, though the measurements are extremely delicate. Atmospheric motion shifts light by small amounts. Winds moving toward or away from an observer change the measured wavelength through the Doppler effect. Spectra can reveal rotation jet streams, rising gas, and escaping material. On hot planets close to their stars, strong winds may carry heat from the illuminated side toward the darker side. Light records these motions through line shifts and changing brightness. In the highest layers, energetic ultraviolet and X-ray radiation can ionize gases. The resulting charged particles form an ionosphere. Radio waves passing through this region experience frequency-dependent delays and bending. Conditions change with stellar activity, time of day, and magnetic disturbances. Communication systems and navigation measurements must account for these variations. Some atmospheres extend outward as escaping envelopes. Light atoms can gain enough energy to rise and drift into space. Strong stellar radiation can drive larger outflows, especially around young or intensely heated planets. Transit observations sometimes reveal extended clouds of hydrogen or other elements far above the visible atmosphere. These signals show that the atmospheric boundary is gradual rather than sharply defined. Within a planetary atmosphere, light follows paths shaped by density composition, clouds, particles, temperature, motion, and ionization. It may bend, scatter, disappear at selected wavelengths, or emerge as new thermal radiation. The local vacuum speed remains unchanged wherever light moves freely, while the atmosphere alters the effective journey through countless interactions. The final signal becomes a layered record of the air it has crossed. Even a clear sky therefore acts as an active optical medium, preserving the history of pressure chemistry, weather, and radiation along every arriving path of light through its layers. Inside transparent materials, light enters matter that appears clear because most visible wavelengths pass through without being absorbed. Glass, water, clear crystals, and certain plastics allow an image or beam to continue across them, yet the journey differs from travel through empty space. The measured speed is lower, the path may bend, and the material can separate. Colors alter polarization or reflect part of the incoming light. A transparent solid or liquid contains atoms and molecules arranged closely together. Their electrons remain bound within the material, but they respond to the changing electric field carried by light. As the wave moves forward, these electrons shift slightly from their usual positions and then return. Their motion produces electromagnetic disturbances that combine with the original wave. The combined result travels through the material at an effective speed lower than the vacuum speed. This process does not require a photon to stop at every atom and wait before moving again. In a uniform substance, light and matter form a coupled electromagnetic response throughout the material. The microscopic interactions alter the phase of the wave, meaning the timing of its repeating pattern. Across many atoms, these changes create the measurable delay. The vacuum speed remains the fundamental local speed between interactions, while the collective response determines how the wave propagates through matter. The refractive index describes how strongly a material reduces the effective speed of light. It compares the vacuum speed with the speed measured in the substance. Air has a refractive index only slightly greater than 1. Water has a larger value and ordinary glass is larger still. The exact value depends on composition, temperature, pressure, and wavelength. When light passes from one material into another, its frequency remains the same, but its wavelength changes. Frequency is the number of wave cycles passing a point during the given time. The source fixes this rhythm, and the boundary does not usually change it. Because the wave travels more slowly inside the material while maintaining the same frequency, the distance between successive wave peaks becomes shorter. A change in speed also changes direction when light enters at an angle. This bending is refraction. A beam entering water from air bends toward the direction perpendicular to the surface. When it leaves the water, it bends away again. A straight object, partly submerged in water, can appear displaced or bent because light from the underwater section changes direction before reaching an observer. Not all wavelengths bend by the same amount. The refractive index usually varies with wavelength, a property called dispersion. In ordinary glass, blue light generally slows and bends slightly, more than red light. A prism, therefore, spreads white light into a band of colors. Each color follows a different path because each wavelength interacts differently with electrons in the material. A rainbow forms through a related process inside water droplets. Sunlight enters, a droplet reflects from the inner surface and refracts again as it leaves. Dispersion separates the colors along different angles. Many droplets contribute light, but only those in suitable positions send a particular color toward the observer. The curved arrangement follows from the geometry of these paths. Reflection occurs whenever light reaches a boundary between materials with different optical properties. Some of the wave returns into the first material while the rest enters the second. Even clear glass reflects a small fraction of visible light at each surface. Multiple panes can produce several faint, reflected images. Coatings with carefully chosen thicknesses reduce reflection by causing returning waves to cancel one another. Transparent materials are never perfectly clear at every wavelength. Glass that passes visible light may absorb much ultraviolet or infrared radiation. Water transmits blue and green visible light more effectively than many red and infrared wavelengths. A material appears transparent only within certain ranges. Outside them, atoms, molecules, or internal vibrations absorb the incoming energy. Internal structure also matters. A uniform crystal can transmit light well while cracks, bubbles, grains, or droplets scatter it. Frosted glass is chemically similar to clear glass, but its rough surface redirects light in many directions. Milk contains tiny droplets and particles that scatter visible wavelengths, making it opaque, even though its main liquid component is water. Transparency depends on composition and on the size and arrangement of irregularities. Some crystals respond differently according to direction. Their atoms are arranged in ordered patterns that are not optically identical along every axis. A light wave entering such a crystal may split into two components that travel at different effective speeds. This property is called birefringence. The two beams can emerge with different directions or polarization, revealing the internal symmetry of the crystal. Polarization describes the orientation of the light's electric field. Certain transparent filters transmit one orientation more strongly than another. Stacked filters can reduce or block light depending on their relative angles. Transparent plastics may also become birefringent when stressed. Under polarized light, internal forces appear as colored patterns because different wavelengths accumulate different phase changes. A short pulse of light behaves more subtly than a steady wave. Different wavelengths within the pulse may travel at different effective speeds. The pulse can spread as it crosses the material, so its leading and trailing parts become separated. The speed associated with the overall pulse is called group velocity. It is usually below the vacuum speed in ordinary substances, though unusual conditions can produce values that seem faster without allowing information to exceed the fundamental limit. Absorption and re-emission can add further delay in some materials. Fluorescent substances absorb light at one wavelength and later release new photons at a longer wavelength. The delay may be brief, yet it is measurable. The outgoing radiation is not the original beam continuing slowly. It is newly emitted light, produced after energy remains within the material for a short interval. Across transparent matter, the apparent slowing of light emerges from orderly interaction rather than mechanical resistance. The material responds to the electromagnetic field, changes the phase and wavelength, and guides the wave along a path determined by its structure. Refraction, dispersion, reflection. Polarization and limited absorption arise from this response. A clear window, therefore, does more than permit light to pass. It reshapes the timing, direction, and form of the radiation while preserving the local vacuum speed as the underlying limit. At the molecular scale, light meets matter through the motion of electrons and through the internal movements of atoms joined together. A molecule is a group of atoms held by chemical bonds. These bonds are not rigid rods. The atoms vibrate, rotate, and shift in response to energy while their electrons occupy allowed patterns around the nuclei. Light interacts with these motions only when its frequency matches an available change within the molecule. The electric field of light pushes on charged particles. Electrons respond most strongly because they are light and mobile compared with atomic nuclei. In a bound molecule, however, an electron cannot take any arbitrary amount of energy. It can move only between permitted energy states. When a photon carries the right energy, the molecule may absorb it and enter a higher state. If the photon energy does not match an allowed transition, the light is more likely to pass through, scatter, or interact weakly. Different forms of molecular motion correspond to different ranges of light. Rotational motion often interacts with microwave radiation. Vibrational motion commonly interacts with infrared radiation. Changes in electronic structure usually require visible or ultraviolet light. These ranges overlap in complex molecules, but the broad pattern allows spectra to reveal what kinds of motion are occurring inside matter. A rotating molecule changes its orientation in space. Its allowed rotational states depend on its mass and shape. Molecules with uneven electrical charge distributions interact especially well with microwave radiation. When the frequency matches the difference between two rotational states, the molecule absorbs energy. The resulting spectral lines can identify gases in planetary atmospheres, interstellar clouds, and laboratory samples. Vibration involves atoms moving relative to one another while remaining chemically bonded. A simple bond may stretch and compress. A group of atoms may bend, twist, or rock. Each pattern has a characteristic frequency determined by atomic masses and bond strength. Infrared light can excite these vibrations when the changing motion also changes the molecule's electric charge distribution. Water, carbon dioxide, methane, and many other gases absorb infrared radiation because their vibrations interact with the electromagnetic field. The absorption occurs in bands rather than at one single wavelength because rotation accompanies vibration and because collisions broaden the transitions. These bands shape the transfer of thermal radiation through atmospheres and other materials. Molecules also emit infrared light. After collisions or absorption, place a molecule in an excited vibrational state, it can release a photon and return to a lower state. The emitted wavelength carries information about the energy difference. In dense matter, energy may instead pass into neighboring molecules through collisions before radiation escapes. Temperature, pressure, and composition therefore influence both the strength and shape of molecular spectra. Visible and ultraviolet photons can move electrons into higher molecular states. In molecules, electrons occupy orbitals that extend across one or more chemical bonds. An orbital is a quantum description of where an electron is likely to be found and how it behaves. Absorption changes the distribution of electronic probability rather than moving a tiny object along a fixed path. Some electronic transitions produce color. A substance appears colored when it absorbs certain visible wavelengths more strongly than others. The remaining transmitted or reflected light reaches the eye or instrument. Chlorophyll absorbs strongly in blue and red regions while reflecting more green light. Many minerals, pigments, and organic compounds gain their color from related electronic transitions. After absorbing visible or ultraviolet light, a molecule can lose energy in several ways. It may release a photon quickly through fluorescence. It may enter a longer-lived state and emit later through phosphorescence. It may transfer energy into vibration and heat. It may also undergo a chemical reaction if the absorbed energy weakens or breaks a bond. The outcome depends on molecular structure and surroundings. Fluorescence illustrates why delayed emission does not represent a photon traveling slowly inside matter. The incoming photon is absorbed and no longer continues. The molecule remains excited for a brief interval, then emits a different photon. The new photon often has lower energy because some energy has already entered molecular vibration. This produces a longer emitted wavelength. Scattering also reveals molecular behavior. In ordinary elastic scattering, the outgoing light keeps nearly the same frequency while changing direction. In Raman scattering, the molecule gains or loses a small amount of vibrational or rotational energy, so the outgoing photon has a slightly different frequency. These small shifts provide a detailed fingerprint of chemical bonds. In liquids and solids, neighboring molecules alter one another's energy levels. Collisions, electrical fields, and structural disorder broaden sharp transitions into wider bands. A crystal may have highly ordered states shared across many atoms, while a liquid constantly rearranges. These differences influence transparency, color reflection, and the effective speed of light. The response of bound electrons also determines refractive index. When the light frequency lies far from strong absorption, electrons shift slightly with the field and return without taking lasting energy. Their delayed response changes the phase of the wave. Near an absorption frequency, the response becomes stronger and more complex. Dispersion increases and absorption may rise sharply. Very intense light can push matter beyond its ordinary linear response. Two or more photons may combine their effects in a single transition, or a material may produce light at new frequencies. These non-linear processes require strong fields, often supplied by lasers. They still obey conservation of energy and the quantum rules governing allowed states. Temperature changes this exchange by altering molecular motion and the number of particles already occupying excited states. At low temperature, most molecules remain near their lowest available energies. At higher temperature, more rotational and vibrational states are populated. Pressure increases, collisions broadens spectral features and can shift them slightly. Careful measurements, therefore, separate molecular identity from the conditions surrounding the molecules in matter. At the molecular level, the speed of light through matter emerges from countless coordinated responses. Molecules rotate, vibrate, shift electron distributions, absorb energy, and release new photons. Some frequencies cross with little disturbance, while others are strongly removed or delayed. The resulting spectrum becomes a detailed map of internal structure. Light does not merely illuminate molecules from outside. Its electric and magnetic fields enter their patterns of motion, and the measured signal records the quiet exchange between radiation and bound matter. At the atomic scale, light interacts with matter through discrete energy levels. An atom contains a nucleus surrounded by electrons described by quantum states. These states are not miniature planetary orbits, they are allowed patterns of energy motion and probability. An electron bound within an atom can occupy one state or another, but it cannot remain between two permitted levels. When light reaches an atom, the electric field of the radiation acts on the electrons. If a photon carries exactly the right amount of energy, the atom can absorb it and move an electron into a higher state. The photon then ceases to exist as a particle. Its energy becomes part of the excited atom. If no suitable transition is available, the light may pass by, scatter, or interact only weakly. The energy difference between atomic states determines the wavelength that can be absorbed. Each element has its own arrangement of states because each nucleus has a particular charge and each atom contains a characteristic number of electrons. Hydrogen, helium, sodium, calcium, iron, and every other element therefore produce distinct spectral patterns. These patterns act as physical signatures rather than labels. An excited atom does not remain excited forever. It can return to a lower state by emitting a photon. The emitted photon carries energy equal to the difference between the two states. Its wavelength is therefore linked to the same atomic structure that governs absorption. In a thin gas, this process creates bright emission lines. In cooler gas placed before a bright continuous source, the same transitions create dark absorption lines. The direction of emitted light is often unrelated to the direction of the absorbed photon. The release may occur after a short delay, and the new photon may have a different polarization. The original photon does not wait inside the atom and later continue its path. Absorption ends that photon while emission creates another. This distinction helps explain why radiation can be delayed or redirected without requiring light itself to move below the vacuum speed between events. Some excited states last only a fraction of a second. Others persist longer because the transition to a lower state is weak or restricted by quantum rules. Such long-lived states are called metastable states. They can store energy temporarily before releasing it through radiation or collisions. Their lifetimes influence the width of spectral lines and the timing of emitted light. A spectral line is never infinitely narrow. One source of width comes from the finite lifetime of the excited state. A short-lived state produces a less precisely defined energy and therefore a broader range of emitted frequencies. Thermal motion adds further broadening because atoms moving toward or away from an observer shift the measured wavelength. Collisions can disturb the energy levels and widen the line again. Resonance occurs when incoming light closely matches an allowed transition. Near resonance, the atomic response becomes strong. The atom can absorb scatter or delay the radiation more effectively than it does at nearby frequencies. In a gas containing many identical atoms, this response can produce a large refractive effect across a narrow wavelength range. The wave phase changes rapidly, even when most photons are not permanently absorbed. Resonant scattering is common in astrophysical gases. A photon excites an atom, and the atom soon emits another photon with nearly the same energy. The new direction is often different. Repeated resonant scattering can trap radiation inside a cloud for a long time. The total distance traveled becomes much greater than the straight path across the cloud, so the energy emerges later and from a different location. Atomic transitions also respond to magnetic and electric fields. A magnetic field can split one energy level into several closely spaced levels. This produces multiple spectral components where one line would otherwise appear. The effect allows magnetic fields to be measured in stars, laboratory plasmas, and other environments. Electric fields can shift and split levels as well, especially in dense gases, where nearby charged particles create local fields. The structure becomes more complex when several electrons occupy the same atom. Electrons interact with the nucleus and with one another. Quantum rules limit which states they can share, and the combined atom develops many possible transitions. Heavy elements therefore produce dense forests of spectral lines. Precise calculations and laboratory measurements are needed to identify them. Ionization occurs when a photon carries enough energy to remove an electron completely from the atom. The photon disappears and part of its energy overcomes the binding of the electron. Any remaining energy becomes motion of the freed electron and the ion. Ultraviolet and X-ray photons ionize atoms efficiently because their energies are high. The resulting plasma interacts with later radiation through both bound and free electrons. The reverse process also occurs. A free electron can join an ion and the combined system releases energy. Some energy appears as a photon, while additional photons may follow as the captured electron moves through lower states. These recombination emissions create characteristic lines in nebulae stellar atmospheres and laboratory discharges. Their intensity reveals temperature density and ionization conditions. Atomic clocks use controlled transitions as stable time references. A microwave or optical field is tuned to match a specific energy difference. The atoms respond most strongly at resonance, allowing the frequency to be measured with great precision. Because frequency counts repeated cycles, a stable atomic transition provides a reliable standard for time. Modern definitions of the second rest on this principle. These clocks also demonstrate the close link between light frequency and time. If two clocks occupy different gravitational conditions or move differently, their measured rates can diverge according to relativity. The atomic transition remains locally consistent while comparisons reveal how space-time affects elapsed time. Light carries the timing signal between the clocks and preserves the causal limit. At the level of individual atoms, the apparent delay of light emerges from excitation, phase response scattering, and re-emission. The atom accepts only selected energies, stores them for characteristic intervals, and releases radiation according to quantum rules. Spectral lines, resonance ionization, and atomic timing all arise from the same discrete structure. Light remains locally governed by the vacuum speed, while atoms determine when energy is absorbed, how long it is held, and in what form it returns to the surrounding field. At the field scale, light is described as a traveling disturbance in electric and magnetic fields. An electric field represents the influence that electric charge can exert across space. A magnetic field represents the influence associated with moving charge and magnetism. In light, these two fields change together and carry energy through a vacuum even when no material substance is present. A changing electric field produces a changing magnetic field, and a changing magnetic field produces a changing electric field. This mutual relationship allows the disturbance to continue moving after it leaves its source across the surrounding empty space. The fields do not require air, water, glass, or any other medium. They exist as physical features of space and evolve according to the laws of electromagnetism. The classical description is expressed by Maxwell's equations, a set of relations connecting electric charge, electric current, electric fields, and magnetic fields. These equations show that changing fields can form waves. The calculated speed of these waves depends on two properties of empty space called electric permittivity and magnetic permeability. Their measured values lead to the same speed observed for light in a vacuum. This agreement reveals that visible light is one part of the electromagnetic spectrum. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays all share the same basic field structure. They differ mainly in frequency and wavelength. In empty space, every part of the spectrum travels at the same local speed. An electromagnetic wave is transverse. This means that the electric and magnetic fields oscillate in directions perpendicular to the direction of travel. The two fields are also perpendicular to each other. Their coordinated changes move forward through space while carrying energy and momentum. The fields do not sweep material particles along with the beam in the way a water wave moves through water. The frequency of the wave describes how rapidly the fields repeat their pattern. The wavelength describes the distance between successive repetitions. In a vacuum, frequency multiplied by wavelength gives the speed of light. A higher frequency therefore corresponds to a shorter wavelength, while a lower frequency corresponds to a longer wavelength. The speed remains the same because these two quantities change together. The amplitude of the field relates to the intensity of the radiation. A stronger electric and magnetic field carries more energy across a given area. Bright light has greater intensity than dim light, but brightness does not change the vacuum speed. A weak radio signal and an intense gamma ray burst both propagate locally at the same limiting speed when they move through empty space. Polarization also follows naturally from the field description. It specifies the orientation in which the electric field oscillates. In linearly polarized light, the field maintains one preferred direction. In circularly polarized light, the field direction rotates steadily as the wave advances. More complex patterns are also possible. Reflection scattering magnetic environments and specially designed materials can alter polarization. The fields carry momentum as well as energy. When light strikes matter, it can exert pressure. This radiation pressure is usually small, but it becomes measurable with sensitive instruments and intense beams. Sunlight can push on dust grains and influence the tails of comets. It can also provide thrust to a reflective sail in space. The effect follows from the transfer of electromagnetic momentum to matter. Energy flows in the direction of the traveling wave. When waves overlap, local flow can become more complicated, but total energy remains conserved. Interference occurs when two or more waves overlap. Their electric and magnetic fields add together. If corresponding parts of the waves align, the combined amplitude increases. If opposite parts align, the fields partly or completely cancel. The resulting pattern contains bright and dark regions. This does not mean that energy disappears permanently in the dark regions. It is redistributed across the wider pattern. Diffraction is another field effect. When light passes through a narrow opening or around an edge, the wave spreads. The amount of spreading depends on the relation between wavelength and the size of the opening or obstacle. Long wavelengths bend around large objects more readily than short wavelengths. Radio waves can therefore pass around hills and buildings more effectively than visible light. The field description also explains why a beam cannot be confined to a perfectly narrow line. over an unlimited distance. Any finite beam spreads because its different wave components travel in slightly different directions. Lenses and mirrors can focus light, but even an ideal optical system is limited by diffraction. The smallest possible focused region depends on wavelength and on the geometry of the instrument. In empty space, electromagnetic waves obey a highly stable pattern of propagation. They can cross enormous distances without losing speed. Their intensity falls when the energy spreads over a larger area, not because the field becomes tired or because the vacuum absorbs ordinary light. Absorption requires interaction with matter background radiation under suitable conditions or curved space-time that changes the path. The vacuum itself is not treated as a mechanical substance with a preferred state of rest. 19th century models once proposed an invisible medium called the luminiferous ether, but experiments failed to reveal the expected motion relative to such a medium. Modern physics instead describes the speed of light as a property of space-time and electromagnetic law, not as a speed measured against hidden material. Different observers, moving uniformly relative to one another, measure the same vacuum speed for light. Their measurements of distance and time adjust according to relativity, preserving this result. The field pattern remains consistent with the causal structure of spacetime. No ordinary signal carried by an electromagnetic disturbance outruns the limiting speed. Classical electromagnetism describes propagation, reflection, refraction, interference, diffraction, and polarization with remarkable accuracy. It treats light as a continuous field and predicts how that field changes from place to place. At this inner field layer, light no longer appears merely as brightness crossing a distance. It becomes a coordinated pattern of electric and magnetic change, carrying energy and momentum through space without a material carrier. Its speed emerges from the structure of electromagnetic law and the measured properties of the vacuum. The traveling field connects source and destination through a continuous local process, preserving the same limiting speed across every empty region it enters. At the quantum scale, light is described through photons and through a mathematical field that gives probabilities for what may be observed. A photon is the smallest discrete amount of energy associated with electromagnetic radiation. It is not a tiny glowing ball following a hidden classical track. It is a quantum excitation whose behavior depends on how it is produced, how it travels, and how it is measured. Each photon carries energy related to its frequency. Higher frequency light carries more energy per photon, while lower frequency light carries less. A gamma-ray photon, therefore, carries far more energy than a radio photon. Brightness can increase because more photons arrive, because each photon carries more energy, or through a combination of both. The speed in vacuum does not depend on the photon energy. Photons also carry momentum even though they have no rest mass. When they strike matter, they can transfer this momentum and produce radiation pressure. A single transfer is extremely small, but many photons acting together can push microscopic particles, move delicate laboratory mirrors, and provide gradual thrust to a reflective sail. Momentum conservation remains valid in every absorption, emission, and scattering event. Quantum theory preserves the wave behavior described by electromagnetism while adding discrete detection events. Light spreads, interferes, and diffracts like a wave, yet a detector records localized exchanges of energy. In a sensitive instrument, individual photons arrive as separate signals. Over time, many detections build the same interference pattern predicted by a continuous wave. A double-slit experiment reveals this combination clearly. When light passes through two narrow openings, the probability of detection varies across the screen. Bright regions contain many detections, while dark regions contain few or none. Even when photons are released one at a time, the complete pattern gradually appears. Each photon is detected at one place, but the distribution of many events follows wave-like interference. Quantum theory does not assign a definite classical path to the photon between source and detector unless an interaction establishes path information. The calculation includes all available alternatives and combines their probability amplitudes. A probability amplitude is a mathematical quantity that can reinforce or cancel another amplitude. The final detection probabilities arise from this combination. When an experiment determines which slit the photon crosses, the interference pattern disappears. The loss does not require a conscious observer. It results from a physical interaction that records path information in the surrounding apparatus or environment. The photon becomes entangled with that record. Entanglement means that the quantum description of one system becomes linked with the description of another. Environmental interactions explain why large objects rarely display obvious quantum interference. Air molecules, thermal radiation, and internal motion continually carry away information about position and motion. This process is called decoherence. It suppresses observable interference between alternatives without changing the underlying quantum laws. For photons, traveling through a clean vacuum coherence can persist across very long distances. A photon can be absorbed only as a whole in an ordinary single photon event. An atom does not take half of one photon while the other half continues. The probability wave may extend across a broad region, but detection transfers one discrete amount of energy at one location. Repeating the experiment produces different individual outcomes while preserving a stable statistical pattern. Emission is also quantum. An excited atom can release a photon when it moves to a lower energy state. The photon frequency reflects the difference between the two states. Its direction and polarization are described by probabilities shaped by the atom and its surroundings. The exact moment of spontaneous emission cannot be predicted for one atom, though the average behavior of many identical atoms can be described precisely. Stimulated emission occurs when incoming light encourages an excited atom to release a second photon with matching frequency phase direction and polarization. Lasers use this process to build highly ordered light. The resulting beam contains many photons occupying closely related quantum states. Its narrow direction and stable phase make it useful for measurement, communication, surgery manufacturing, and fundamental experiments. Photons are identical particles. No intrinsic label distinguishes one photon from another. Their collective quantum behavior follows rules associated with particles called bosons. Many photons can occupy the same state, allowing intense coherent fields to form. This property supports laser action and helps connect the quantum description of photons with the classical description of electromagnetic waves. Polarization also has a quantum form. A photon can be prepared so that measurement has several possible polarization outcomes. Before measurement, the state can contain a combination of alternatives. The detector produces one definite result, while repeated measurements reveal the predicted probabilities. Carefully prepared pairs of photons can possess entangled polarizations whose correlations remain stronger than any local classical model allows. These correlations do not permit messages to travel faster than light. Each local result remains unpredictable, and useful information appears only after ordinary records from separated measurements are compared. That comparison must travel through a conventional causal channel at or below the speed of light. Quantum entanglement changes the structure of correlations without creating faster-than-light communication. In quantum electrodynamics, light and charged matter are treated as quantum fields. Quantum electrodynamics is the theory describing interactions between the electromagnetic field and particles such as electrons. It predicts experimental results with extraordinary precision. Processes that appear simple at large scales emerge from sums over many possible quantum interactions. A photon traveling through vacuum does not repeatedly collide with hidden material. The quantum field evolves according to the structure of space-time and the rules of the theory. Vacuum is not simple nothingness, but its quantum properties do not provide a preferred frame that slows ordinary light. Measurable propagation remains consistent with the invariant vacuum speed. Its quantum description does not weaken causal order. Every controllable influence still travels through fields and interactions whose observable effects remain bounded by the same space-time structure that governs classical radiation across vacuum and matter at every measurable scale. At the quantum scale, light is neither only a classical wave nor only a stream of tiny objects. It is a quantum field whose excitations arrive in discrete exchanges while spreading according to probability amplitudes. Interference, entanglement, absorption, emission, and polarization belong to one coherent description. The speed of light remains the limit connecting all possible preparations, interactions, and measurements across space-time. At the deepest established description, the speed of light in vacuum is not merely a very large speed assigned to one kind of radiation. It is a universal constant built into the structure of space-time. Every observer moving at a steady speed measures the same vacuum speed for light, even when the source and observer move relative to one another. This result differs from ordinary experience, where measured speeds usually add or subtract according to motion. The invariant speed is about 299,792 kilometers per second. In modern measurement, this value is exact because the meter is defined through the distance light travels in vacuum during a specified fraction of a second. The second is defined using a precise atomic transition in cesium. Length and time standards are therefore joined through light and atomic frequency. Earlier measurements treat the speed of light as an unknown quantity. Astronomical observations provide the first convincing evidence that it is finite. Changes in the observed timing of eclipses among Jupiter's moons reveal that light requires more time to cross a larger distance. Later experiments use rotating wheels, mirrors, long paths, and increasingly stable clocks. Each method improves precision and confirms that light does not arrive instantaneously. Interferometers provide another sensitive approach. An interferometer divides light along separate paths and then recombines it. Small differences in travel time alter the resulting interference pattern. Experiments searching for changes caused by motion through a supposed light-carrying medium fail to find the expected effect. These results weaken the older ether model and support a description without a preferred state of rest for the vacuum. Special relativity places the invariant speed at the center of its structure. Space and time measurements depend on the relative motion of observers. Two observers can disagree about the length of an object, the duration between events, or whether separated events occur at the same time. They still agree on the vacuum speed of light. The changes in measured distance and time preserve that common result. Time dilation follows from this structure. A moving clock is measured as running more slowly than a clock at rest relative to the observer. Length contraction also occurs along the direction of motion. These effects are not mechanical damage or optical illusion. They are consistent differences in the way space-time intervals are divided into measured space and measured time. Relativity of simultaneity is equally important. Events that are simultaneous for one observer may occur at different times for another observer, moving relative to the first. No universal present extends through all of space in the ordinary sense. The invariant speed defines how observations from separated places can be compared without contradicting causal order. Light cones express this order geometrically. Events inside a future light cone can be influenced by a signal from the present event. Events inside a past light cone can influence it. Events outside both regions are separated in a way that prevents any signal at or below the invariant speed from connecting them in time. This division remains the same for all observers, even when they disagree about distances and durations. Objects with rest mass cannot be accelerated to the speed of light. As a massive object moves faster, additional energy produces progressively smaller increases in speed. Reaching the invariant speed would require unlimited energy. Photons travel at this speed in vacuum because they have no rest mass. Other massless field disturbances also follow the same causal structure. Nothing in this description prevents a distant separation from increasing faster than light through cosmic expansion. It also does not forbid a spot of light or a geometric shadow from sweeping across a remote surface faster than light. Such patterns do not carry matter or controllable information between neighboring points at that rate. The local transfer of cause and effect remains limited. Measurements of high-energy photons test whether different photon energies travel at slightly different vacuum speeds. Observations of brief events across great distances place very strong limits on such differences. Within present sensitivity, light of different frequencies follows the same vacuum speed. It remains uncertain whether future theories of quantum gravity will predict extremely small departures under conditions not yet accessible, but no confirmed observation requires such a change. Gravitational waves provide another test of the causal limit. These disturbances in space-time propagate at the same fundamental speed within measurement uncertainty. When light and gravitational waves arise from the same distant event, their arrival times can be compared after accounting for different emission processes and paths. The agreement supports the shared structure predicted by general relativity. In curved spacetime, a single global speed, expressed as distance divided by one universal time, can become coordinate-dependent. Coordinates are labels used to describe events, and different choices can assign different apparent rates to distant motion. Local measurement remains decisive. In every sufficiently small, freely falling region, light in vacuum passes a nearby observer at the invariant speed. Practical systems depend on this framework. Satellite navigation compares signals from moving clocks at different gravitational heights. Special and general relativistic corrections are required for accurate positioning. Radar, ranging, spacecraft communication, radio astronomy, and precision timing all rely on finite signal travel and on stable electromagnetic propagation. The speed of light also connects units observations and causality. It converts intervals of time into intervals of distance and links energy with mass in relativity. Its role extends beyond visible light because every electromagnetic frequency and every causal influence in established local physics obeys the same limit. At this final layer, the truth about the speed of light rests in consistency rather than mystery. Light does not race through space against a hidden background. Space and time adjust together so that its vacuum speed remains unchanged for every local inertial observer. Measurements from laboratories, spacecraft, atomic clocks, astronomical events, and gravitational waves converge on the same structure. That limit remains stable across every tested inertial frame today. The constant, therefore, acts as more than a property of photons. It defines the boundary between events that can exchange information and events that cannot yet be connected. Across every scale, from the observable universe to individual quantum interactions, distance and duration meet at this limit. The speed of light remains the steady measure by which physical influence moves through space-time. Across the darkness between stars and the quiet spaces within matter, light continues to follow the same measured order. It leaves distant galaxies, crosses expanding space, passes through clouds of gas and dust, enters atmospheres, bends through water and glass, and meets the structured energy levels of atoms. Along each path, its direction, wavelength, intensity, and arrival time may change. The underlying limit remains steady. Every image carried by light belongs to an earlier moment. A nearby surface appears after a delay too small for ordinary senses to notice. A planet appears minutes or hours in the past. A star appears years ago. A remote galaxy arrives from an age when the universe holds a different form. Light joins distance with memory, allowing the present to contain quiet records from many times. Matter receives this radiation and reshapes it. Some photons scatter and continue along new paths. Some disappear into atoms and molecules, leaving their energy behind. New photons later emerge with different wavelengths and directions. Other waves pass through almost unchanged, preserving details of the place where they begin. The final signal carries both its source and the history of the regions it crosses. The constant speed in vacuum remains part of the structure of space-time itself. It orders cause and effect, defines the reach of information, and gives physical meaning to cosmic horizons. No observer occupies a preferred state of rest, and no ordinary message outruns this boundary. As the wider universe settles into darkness, light remains in motion through every transparent interval. Its passage is silent, finite, and precise. Distance continues to become time, and time continues to become the record carried by light.